All right, guys, so this is the last section for chapter 2. Now, you actually also have a 2.6 section, which is not required for us to do. So this will be the last section that you guys do in my math lab also for homework. But if you were to look at your textbook, you'll see there's an additional section that we're not actually covering. So this one here is talking about the inverse functions. When we're talking about inverse functions, we're basically talking about if one function is doing, let's say, addition, then the inverse function is going to undo what the addition function did, right? So what would be the inverse function for addition? Subtraction. What would be the inverse function for a cube root? A cube. Yeah, because a cube will undo what a cube root did, or vice versa, right? A cube root is going to undo what a cube did. Just like with multiplication, your inverse would be division, and of course that relationship also is vice versa. So the idea is, if they're simple operations, you can find the inverse, because addition will have subtraction, a fourth root will have the fourth power, stuff like that. But what happens when you start combining operations? So if you did both addition and, let's say, a square within the same function, well, we know for addition, subtraction is going to be the inverse. We know for the square root is going to be the inverse. But then again, your order is going to be really, really important in an inverse function, because now I'm doing two operations. I could be doing 3 or 4 operations within the same function. So in what order do you find the inverse? So that's kind of what we're looking at here. Now, the first thing you have to do when you're working with inverse functions is make sure the functions are one-to-one, which is a relationship between, you can think about it as being relationship between the x and y values. And you have to make sure that you will actually be able to find the inverse of this function. So we say make sure your function is invertible. So we're actually starting out with a pretty simple example here to kind of illustrate this. So we have a pizza example. We're saying we want to order a pizza. If you get a plain cheese pizza, you're paying $5. If you want to get any additional toppings, you start paying $2 for each additional topping. So if you think about as the cost of the pizza being our x values and y representing the number of toppings, then the idea here is if I know the cost of the pizza and I know it's going to be $2 for each topping, from looking at the x value, I should be able to find my y value, right? So if we're paying $13, I know $5 is going to be for the base cheese pizza, right? Basic, no toppings, nothing. So that means if I'm paying $13, how much extra am I paying to get toppings on there if $5 is the base price? $7, right? No. $8. So how many toppings are we getting? $2 a topping. So you're getting 4 toppings. You should be able to make that calculation happen. The other important thing here is you should see that these ordered pairs are unique. There's no repetition, right? With $5, I'm only getting cheese pizza. I'm not getting any toppings, so that's 0 toppings. At $7, it's 1 topping. At $9, it's 2 topping. Unique relationship between the x value and the y value. This is very, very crucial when we're talking about this one-to-one correspondence. So for every cost, there is a unique number of toppings. For every topping, there is a unique cost. So it's not like I can pay $13 and I can either get 4 toppings or 5 toppings, right? At $13, I'm only going to get 4 toppings. If I want 5 toppings, I got to pay $2 more, right? It's got to be 15 then. That's the unique relationship we're talking about. There's no repetition happening in the sense of for the same x, there's no 2 different y's. For the same y value, there's no 2 different x. If you think about going back to our function definition, we're kind of building up on that. So we're saying there's a one-to-one correspondence between the x and the y values, or between the domain and the range of this function. And we can say the function is one-to-one. This is very, very important. Again, if you're going to be able to find the inverse of a function, functions have to be one-to-one. Now they're thinking about an example which is not one-to-one, and you can, again, since we're talking in terms of food. You can think about the dollar menu, and we're listing McDonald's, Wendy's, Taco Bell. I honestly don't know if all of those restaurants have a dollar menu or not. I just kind of put all the fast food that I could think of. But let's imagine that I know McDonald's does. I think you can get like, or at least you used to get a small fry. I think their drinks are still $1. You could get like a sandwich or something. So what's happening here is there's no unique relationship, right? Like let's say we listed fries, a drink, and maybe a small burger. There's 3 different unique items, but you're still paying the same price, right? You're paying $1 for all of them. So there's not that unique relationship where for $1, I can only get a drink, right? Pay 10 cents extra and you get a fry. Pay, I don't know, another $1 and you get a burger. If there was that unique relationship, we could say these are one-to-one functions, because for the same $1 amount, I can get 3 or 4 different items. So that's why these menus cannot be, the dollar menus cannot be your one-to-one relationship. So we're always looking for this unique relationship. But in this case, we're saying for the one-to-one function, no 2 ordered pairs with different first coordinates and same coordinates. So you cannot have 2 different x values for the same y value. When we defined function back in section 2.1, we said for the same x, we could not have 2 different y, because remember that's where it fails the vertical line test. So this is actually reversing that relationship, and we're saying for the same y value, we cannot have 2 different x, which means you're actually looking at this horizontally. For the same y value, if you imagine this is our y-axis and I'm picking one value on the y-axis, I should not have 2 different x values, and you'll actually see a horizontal line test that we're going to use for this. So in terms of defining if a function is one-to-one, this is the relationship we're looking for, okay? Now going back to our pizza example, see what happens when I switch my x and y values. Now my toppings have become, the number of toppings have become the x values, and the cost for that pizza has become the y, but I still have that one-to-one relationship, right? For number of toppings, I am going to have a unique price. I'm not seeing any repetition on my x values happening. So we actually just created the inverse of that original function that we started out with, where x was the cost, y was the number of toppings. Just literally by switching our x and y table, we have created the inverse function. The other thing you should remember is the first function is the inverse of the other, or vice versa. The second function is the inverse of the first function. This relationship should literally work in both directions. So we're saying if we interchange the x and y coordinates in each ordered pair, we may or may not have a function. But if your original function showed that one-to-one correspondence, then by switching your x and y coordinates, you are still getting a one-to-one function, which means your function is invertible. You can find the inverse of your function. So just as a definition here, the inverse of a one-to-one function f is defined as f inverse. It looks like it's f to the -1 exponent, but you read it as f inverse, okay? And basically you obtain your f inverse function, if we're thinking in terms of ordered pairs, literally just by interchanging your x and y values. Yeah, so this was just me trying to clarify that it's not a negative exponent. That's how we write the inverse notation. So they're actually asking us to think about, will these functions have this one-to-one correspondence? Are these functions invertible? Determine if each function is invertible and give a reason why. So our first example here is talking about the function that pairs the number of days since your birth with your age in years. So think about one variable being defined as the number of days since your birth, and the second variable is your age in years. What kind of a relationship would that have? If I knew one value, would I be able to calculate the other? number of days since you were born and your age in years.
Not sure when we work with decimals.
How old are you?
I am 15.
15? Raylan, how old are you? 20. Okay. Anybody else here who is 15 or 20? 20?
20.
20. Okay. So if you are all 20, does that mean all three of you have the same number of days since you were born? Just tell me your month.
November. June.
August.
Wow, this is perfect. I never get such perfect examples in the class. So this is brilliant. Obviously, none of you are going to have the same number of days since you were born. But what's repeating here? Your age. You're all 20 years old. Now, unfortunately, I will probably not have another person in here who's 15, but that would be the same thing if you looked at your classmates in class, right? Because I would imagine a bunch of you are going to be right around within months of each other, but you're not going to have the same number of days. So that means that since we don't have that unique one-to-one relationship where for 20 years old, you should have only, I don't know, 10,000 so many days, right? Which is not going to be that many, but I'm just throwing a number out there. If it is 21, then it should only be, because basically anybody who is born from January 1st to December 31st in that given year can potentially have the same age, right? And even for that matter, if you are, looking right from this point of October 14th to before or after, if that's your cutoff, you're going to have so many people who are at that same age with not a repetition. So this guy is actually not invertible. Because you're not going to have that unique relationship between your age is a whole number, and you cannot really determine the number of days just by knowing how old somebody is. Okay. Now, example 2, we're talking about a function that's pairing the number of days that a deposit of $100 is earning an interest of 6% compounded daily. So that's one variable, the number of days that this deposit of $100 at 6% interest compounded daily is earning. The amount of interest based on that. So number of days and the amount of interest are actually your two variables here. So what can you say about the relationship between, if I knew the number of days this money had stayed in the bank, would I be able to calculate the amount of interest that $100 earned? Yes? Why?
Because if it's compounding interest, the first day it would become a new amount, and then that amount would compound 6%, and then the new amount then would compound, and each new amount would keep compounding.
Would keep compounding, right? And that's happening because they're specifically telling us that it's compounded daily. If your compounding period was based on weeks or months or years, then the number of days would have no basis on that, right? Because it really depends on what the compounding period is. So since this is compounded daily, then yes, number of days is going to make a huge difference. So in this case, this is an invertible example. So since it's compounded daily, so it basically means number of days can give us the amount of interest. And of course, this relationship will work backwards also, right? Because if I knew how much interest my $100 had earned, I should be able to work backwards and calculate how many days that money has stayed in this account. So remember that one-to-one relationship has to go both ways for your function to be considered as being invertible. So this was just in general terms. Now, going back to our definition where we defined a function being one-to-one as for the same y coordinate, I should not have two different x coordinates. So keeping that definition in mind, what can you tell me about examples 3, 4, 5, and 6? Are they one-to-one, which means can we find the inverse? If we can't find the inverse, they actually want us to write down what the inverse function will be. For the same y value, we cannot have different x values. What's happening on number 3? Same y value, right? And all different x values. So this guy obviously fails that definition. So it's not one-to-one, which means it's not invertible. Okay. 1, 1, 2, 4, 4, 16, 7, 49. For the same y, I cannot have different x values. So will this be considered invertible or not?
Yes.
Yes, it is invertible, and since it is invertible, we can find its inverse, and its inverse, I guess I'm going to write it here, is going to be what?
Right. 1, 1,
Yeah, because even if you interchange them, it stays the same.
4, 2.
4, 2.
16, 4.
16, 4, very good.
49, 7.
Yep, 49 and 7. Oh, I'm running out of space. Okay. We'll just squish it in there. All right, very good, guys. So remember, it's literally just interchanging your x and y coordinates to find the inverse for these examples. What happens with 5? Is it invertible or not invertible? No, because it's actually failing right here in the middle, where for the same y values, I have two different x values. Of course, this guy is not invertible. Okay, very nice. Number 6.
Yes.
It is invertible, right? Because I don't have the same y value with different x. They're all unique. So invertible, and what's our inverse? It is the same. Yeah, because even though you interchange them, since this is coming from an identity function, it really doesn't change anything. Oh, still ran out of space. What? Somewhere. Never mind. We're gonna leave it right there. I'll fix it after class. All right, so we know it's gonna stay the same. So right here, an identity function is the inverse of itself, okay? What's happening with 7? They're saying for the function f, find its inverse. Can we find its inverse? Yes, because for the same y, I don't have different x values. So what will the inverse for this guy be?
-3, -3.
Okay, so that first ordered pair will stay the same.
5, 0.
5, 0, interchange your x and y, and the last one,
-7, 2.
-7, 2. Alrighty. What is f inverse of 5?
0.
Yeah, because you're going to the f inverse function and now finding the ordered pair where your x value is going to be 5, and that's going to be the middle function where your f of inverse of 5 is going to be 0. Okay, very good. Now we're doing a composition between the inverse function and the original function evaluated at 2. So composition, f inverse of f at 2. So that means f inverse is the outside function. F of 2 is the inside function. So what is f of 2 giving us? Go to the f function. What is f of 2? -7, yeah, because that's the ordered pair. So remember, -7 now goes inside of the inverse function. So that's f inverse of -7, and what does that end up giving? 2. And now you have stumbled upon a second property, I guess, of inverse functions is when you actually compose an inverse function with the original function, you actually get an identity. So we started out with the 2, and we actually end up with that same 2. So this ordered pair is going to be 2 and 2. Anytime you take a composition between the original function and its inverse, you are going to get an identity, which means you end up with those ordered pairs being the same. 2, 2, 3, 3, 4, 4, -1, -1, -5, -5. It's always going to give you an identity. And we'll actually look at a theorem for it here. Questions on 7? Okay. All right, let me see what you guys can do for 8. It's very similar to what we just did. So let me see what you guys come up with 8, and then we'll discuss our answers. Let's actually start by writing down our inverse function. Which is, of course, just interchanging our x and y values. So that'll become 1 and 2, 4 and 3, 0 and 4. They're asking us to find h of 3, which means you're going to the original function, finding the ordered pair where your x value is 3 and its partner, which is going to be the 4. They're asking you to find h inverse of 4. So h inverse of 4, of course, that means go to the inverse function, find the ordered pair with the 4 for your x value and its partner, which is going to be the number 3, right? Because they're going to be the reversed ordered pairs. This guy will be 3, 4. This guy will be 4, 3. Okay. Now, for your composition, let's see what happens here. So we've got h of h inverse at 1, which of course will be defined as h on the outside, h inverse of 1 on the inside. So again, we're going to the inverse function. For 1, our answer comes out to be 2. So that's going to be the output, which will become the input for the h function. And then h of 2 will, of course, go back. And you should notice, again, h of 2 will get us back to that 1 that you started out with. So we started out with the 1. We end with the 1. And again, as I was telling you, anytime you do a composition with the function and its inverse, you should get an identity. So you start with the 1, you should end with the 1. If you remember that, your life will become really easy on this section, okay? Let's see. We're talking about, since we are interchanging our coordinate for the ordered pairs, the domain of the F inverse function should basically become the range for the original function. And of course, the range of the inverse function will be the domain of the original function, because you are, as I mentioned, literally interchanging your x and y values. So all the x values become the y values in your inverse function, and all the y values of the original become the x values for the inverse. So you're interchanging your domain and range also for the inverse and the original function. And I kind of mentioned this earlier, that they will be inverses of each other. So f and f inverse, if I give you f inverse as my original function, then of course the f then becomes its inverse, which again makes our life a lot easier. So this is what I was talking about. How can you verify if you have a function which is 1-to-1 or not? Remember, being 1-to-1 means you can find its inverse. It's invertible. So as long as your horizontal line does not cross the graph of your function at more than 1 point, we can say the function is 1-to-1, which means we can find its inverse. And you will notice here, an absolute value function is not 1-to-1 because my horizontal line crosses the graph at 2 points. So since it's crossing the graph at 2 points, this guy is not 1-to-1, which means I cannot find the inverse of an absolute value function. And just think about it, what will undo an absolute value function? Because absolute values are distances, right? We're just interested in how far this number is from 0. Whereas a cube function, you can see it passes the horizontal line test because it only crosses at 1 point. And we know for a cube root is its inverse function. So obviously he has to be invertible. Again, remember in algebra, or mostly in any kind of math geometry, we don't solely depend on just looking at the graph and making our decision. And just to show you why graphs itself are not going to be good enough, let's look at the graph of this function x cubed minus 0.01x. If you leave your screen on, let's say we're just using a graphing calculator here, doesn't it look like a cube root function, which means it should pass the vertical line test? But look at this screen here. This is from 10 by 10 screen. But now if we zoom in, which is a 0.2 on the x-axis and then 0.001 on the y-axis, you'll notice how it's doing that little wave, and it's definitely going to fail the horizontal line test, because if I draw a horizontal line, it's going to cross my graph at 3 points. Definitely fail. So we don't want to depend just visually on the horizontal line test to help us out. So what we actually do here is we try and see what happens if we put in 2 different x values. And remember, the definition of a 1-to-1 function is for the same y value. I cannot have 2 different x values. So the idea is, if I start by putting in 2 different x values, do I actually get the same y value or not? And that's how we can actually algebraically prove if our function is 1-to-1 or not. Okay, so just as an example here, they're actually using x equals +1 and -1 in our 5x squared function. And of course, because of that square, both our signs will become positive, and you end up getting 5 times 1, which is 5, 5 times -1 squared, which is also +5. So for the 2 different x values, I still have the same y, which is where my 1-to-1 property fails. This function, of course, is a parabola, right? Opening up 5x squared, we know it's going to fail the horizontal line test also. So all parabolas are not invertible. You cannot find their inverses unless we restrict their domain. That's something we're going to look at as we go forward. But let's talk about how to decide if our functions are 1-to-1 or not depending on the graph. So let's look at this guy here. This one was number 9. So this is the g of x function, x plus 2 over x minus 3. Now we don't really want to pick a number for x, and like they did with that 5x squared example with the positive 1 and negative 1, we're going to do this more in the sense of generic terms. So I am actually going to use x sub 1 as my 1x value and x sub 2 as my other one, and we have to prove that they're actually the same x value, and that's how we know this function is 1-to-1. But if we cannot prove that x1 is equal to x2, that means this function is not 1-to-1. So our goal ultimately is at the very end to get x1 equals x2. That's how I know that this function is 1-to-1. If I don't get x1 equals x2, it's not a 1-to-1 function, which means there's no inverse for this guy. So bear with me. Let me show you how this goes. So we're actually saying take the g function and replace your x with x sub 1. So in my function definition, that will actually become x sub 1 plus 2 divided by x sub 1 minus 3, and repeat the same thing on the other side with x sub 2. So equal to x sub 2 plus 2 divided by x sub 2 minus 3. Since this is one fraction on the left, one fraction on the right, I can actually use cross product to simplify these guys out. So that will end up giving us x sub 1 plus 2 multiplied with x sub 2 minus 3. So again, cross product, we are doing x sub 1 minus 3 multiplied with x sub 2 plus 2. What do we end up doing with each of those parentheses? Yeah, you're going to need to FOIL basically both sides of your equation here. So that means I'm going to end up getting x1 times x2. x1 times negative 3 will be negative 3x1. 2 times x2. And then positive 2 times negative 3 will give you negative 6. So remember, each term you need to multiply. Same thing on the right hand side. What will that give us? What do we have on the right hand side? x1 times x2, right? Same thing, x1 times positive 2, negative 3 times x2, and then same thing, negative 3 times positive 2 is negative 6. If you did this correctly, a whole bunch of your terms should cancel out as you try bringing your like terms together. So obviously, I've got x1, x2 here, x1, x2 on the other side. Start by subtracting those. And here's the part I was talking about. A lot of these should cancel each other out. I've got a minus 6, so I can go ahead and add that. So again, your plus 6 minus 6 cancel each other out. Now, I've got a negative 3x1 plus 2x2 left behind on the left, and positive 2x1 minus 3x2 left behind on the right. These guys, of course, you can see are not going to cancel each other out, so let's combine like terms.
You'll be left with negative x of 1 equals negative x of 2.
Yeah, you should end up actually cleaning up pretty nicely. So let's see if I start by moving the 2x1 by subtraction. These guys will cancel out. I'm moving 2x2, which actually should be minus 2x2. These guys cancel out, leaving us behind with, what's that, negative 5x1?
Yes.
And negative 5x2. Divide both sides by negative 5. This is kind of what we were hoping for. You now have x1 equals x2, which is what we wanted. If we get this, that means our functions are 1-to-1, which also means our function is invertible. So it takes a little patience going through these math, just because, you know, we are doing this not with numbers and in generic terms with x sub 1 and x sub 2, but most of the times, 99.9% of the times, they will end up being equal to each other. If they're not, I will show you an example what happens. Question on number 9. Okay, let's see what do we got next. Okay, so we have k of x equals cube root of x plus 9. So let's see how we can prove if this guy is 1-to-1 or not. Cube root of x plus 9. So in that same way as we did number 9, we will start with k of x sub 1 equals k of x sub 2. This will of course become cube root of x sub 1 plus 9 equals cube root of x sub 2 plus 9. What should we do next to clean up our equation? If we have cube roots, yeah, you cube both sides. Just like if you had a square root, you would square both sides. So in that same way, go ahead and cube both sides of your equation. The cube will cancel out the cube root. And this one actually cleans up pretty nicely because now you end up with x1 plus 9 equals x2 plus 9, right?
And then subtract 9, you get x1.
There you go. Yeah, so it starts out looking pretty scary, but it's not that bad. And again, since we can prove that they are equal to each other, that again means our functions are 1-to-1. Which means we can find its inverse. It's invertible. Yes.
One question. For that
Sure.
one, I know we won't ever really have an example like that where it was the x cubed minus the 0.01x.
Yeah.
Doing this would have proved that it wasn't that kind of function, right? Like
If you did the x sub 1, x sub 2, yes. You should not be able to show x1 equals.
it sounds like I said, don't just guess on like try a number because it wouldn't work for that.
Yeah, yeah, definitely. Okay, very good. Any other questions on this guy here? Okay, so what did we say about absolute value functions?
They can't be.
They can be 1-to-1, right? Because absolute value we know is going to have that V shape, which means it is definitely going to fail the vertical line test. Now, interestingly enough, if we're trying to prove with an absolute value function if it is 1-to-1 or not, this method that we just looked at with x sub 1 and x sub 2 does not work. Because what's going to happen is you will end up getting x sub 1 plus 1 in the absolute value equals x sub 2 plus 1 in absolute value. But remember, there's really no way to get rid of absolute value. So that method doesn't work, which means we actually do fall back to just plugging in numbers and showing that for the different x values, I will still end up getting the same y. So any ideas on what numbers we can use here?
You could use 1 and -3.
-3?
Yes.
Yeah, that works. So let's see what happens when I put 1 in. So with 1, it's 1 plus 1. Absolute value of 2 and absolute value of 2 is 2, right? So when I put in 1, I got 2 as my answer. Now what happens with this other x value? Absolute value of -3 plus 1 will give me what? And absolute value of -2 is +2. And look at the ordered pair. For the same y values, I have 2 different x values, right? So some of these functions, you can plug in different numbers for x and see, show that you're getting the same y value. But like the other 2 examples we saw, cube root might have been not that bad, but the x plus 2, x minus 3 would have been challenging. So the algebraic method does work out a little bit better. Man, we literally have like a tiny portion of this left, but obviously we are going to try and finish that before you guys take your exam. And I was really hoping to give you this exam on Wednesday, but I guess we'll move it to Monday. Monday, whatever that date is, add 7 to today's date. 21st.
So you're gonna change the.
I will change the homework date, yes. So you will now have till evening of the 21st to finish your homework. Just don't procrastinate, people. Please do not procrastinate. Like, yay, I got a week. I'm not going to do homework tonight.
I was actually going to do this section and like the last section. Either way, I was so
Okay.